Welcome to this Swagelok video. Today's topic is considerations in managing the supply pressure effect of a regulator. System operators running a process from a gas cylinder source sometimes observe the phenomenon of outlet pressure increasing in a pressure-reducing regulator for no apparent reason. As the cylinder drains, the inlet pressure to the regulator decreases. You might expect the outlet pressure to also decrease, but in fact, the outlet pressure rises. There are a number of possible causes, but the most likely is supply pressure effect, or SPE, sometimes also referred to as dependency. Supply pressure effect is defined as the change in outlet pressure due to a change in inlet or supply pressure. If the inlet pressure decreases, there will be a corresponding outlet pressure increase. Conversely, if the inlet pressure increases, the outlet pressure will decrease. Inlet and outlet pressure changes are inversely proportional to each other. A regulator's supply pressure effect value is typically provided by the manufacturer and can be published as either a percentage or as a ratio. Supply pressure effect in a single-stage regulator occurs whenever there is a change in inlet pressure. However, it may only be noticeable when the change is significant. For example, when a gas cylinder has drained and the pressure dropped from 172 bar to 34 bar, or 2500 psig to 500 psig. The degree of outlet pressure variation for a regulator can be estimated with this formula. For example, for a regulator with a supply pressure effect, or SPE, of 1%, as a cylinder empties from 172 bar to 34 bar, or 2500 psig to 500 psig, the regulator's outlet pressure will increase by 1.3 bar, or 20 psig. One of the most common types of regulators is a spring-loaded pressure-reducing regulator. A spring applies force on a sensing element, either a diaphragm or a piston, which moves the poppet closer to or away from the orifice to control the outlet pressure. In an unbalanced poppet design, the inlet pressure pushes up on the poppet, applying pressure to a portion of the poppet equal to the seat area. As a result, a decrease in inlet pressure means less force is pushing up on the poppet. With the decrease in force, the poppet moves away from the seat, which increases the outlet pressure. The rise in outlet pressure is not strong enough to counterbalance the set spring force to push the diaphragm up to close the poppet at the same outlet pressure. It will close at a higher pressure. Let's demonstrate that by gradually decreasing the inlet pressure of the spring-loaded pressure-reducing regulator. As you can see, at an inlet pressure of 80 bar, or 1160 psig, the outlet pressure is 3.0 bar, or 43.5 psig. Decreasing the inlet pressure to 70 bar, or 1015 psig, results in a higher outlet pressure of 3.3 bar, or 47.9 psig. Moving down to 60 bar, or 870 psig for the inlet pressure causes an outlet pressure of 3.7 bar, or 53.7 psig. And finally, an inlet pressure of 50 bar, or 725 psig leads to an outlet pressure of 4.0 bar, or 58.0 psig, the highest of the process. For many applications, especially high-flow applications, a common method for reducing supply pressure effect is to use a regulator with a balanced poppet design. The objective of this design is to allow the inlet and outlet pressures to control the poppet more evenly, which is accomplished by the O-ring around the lower stem of the poppet and the orifice in the poppet that runs vertically from top to bottom. Returning to the supply pressure effect scenario, we have the inlet pressure decreasing as the gas cylinder is depleting. The inlet pressure has less effect on the poppet because it is acting on a smaller area. The outlet pressure has sufficient leverage to close the poppet and restrict pressure, correcting much of the rise in pressure downstream. Let's demonstrate that by repeating the gradual decrease of the inlet pressure performed earlier, now with a balanced poppet regulator. At an inlet pressure of 80 bar, or 1160 psig, the outlet pressure is 3.0 bar, or 43.5 psig. Decreasing the inlet pressure to 70 bar, or 1015 psig, results in an outlet pressure of 3.1 bar, or 45 psig, still an increase, but a smaller one than occurred with the other regulator design. Moving down to 60 bar or 870 psig for the inlet pressure causes an outlet pressure of 3.2 bar or 46.4 psig. And finally, an inlet pressure of 50 bar or 725 psig has an outlet pressure that is also 3.2 bar or 46.4 psig. Notice how the effect on the outlet pressure is lessened from the previous regulator arrangements.